Now, why do we have to study thermodynamics? That's the question. It is clear. See, what happens is, one of the most important, use of matter that we have is, some matters are used to produce energy. And energy runs the whole cycle in this world. Basically, the industrial cycle, the life cycle, everything. You are alive because you are burning carbohydrates, which we learnt in biomolecules. Then industries are running because they are burning fuel. Okay. Whenever there is a concept of energy. See, I am not using the word heat. The word heat means flow of energy. So understand this point very clearly, that heat means flow of energy. Heat means flow of energy. Now the study of this flow of energy, one of the aspects of this study of flow of energy is thermodynamics. So what encompasses thermodynamics? Study of thermodynamics encompasses includes three aspects. First is, we are trying to understand the concept of energy and work. Energy and work. Then the second point is, so what is energy and work? You are supplying energy to do some mechanical work, electrical work, some work. But here we are mostly talking about mechanical work. You are burning a fuel and making the machine do a mechanical work. This is clear. The second is, we are going to talk about enthalpy change. We are going to talk about enthalpy change. What do you mean by enthalpy change? The change in the heat content. Suppose you are burning coal, it is releasing some energy. If you are melting ice, it is absorbing some energy. So burning coal is a chemical reaction. There is an energy change involved in that. We call it as enthalpy change. When ice is melting, it's a physical change which involves an absorption of certain amount of energy. That's called as enthalpy. So enthalpy changes during physical and chemical changes. The third aspect that we have to study in thermodynamics is, we have to study about spontaneity of a reaction. So what does the word spontaneity mean? The word spontaneity means that the reaction happens on its own. We always say that we keep phosphorus under water, sodium under kerosene. The moment we remove sodium, what happens? It immediately, spontaneously, on its own. Spontaneously means on its own. On its own, it reacts with air to form sodium oxide. Phosphorus, when you remove from water, yellow phosphorus, it immediately forms phosphorus pentoxide. Chemical change has taken place. You didn't do anything. Or you could have rusting of iron. It has taken its own pace. In 2 years, your iron grill has got rusted. 2 years. But it happened on its own. You wouldn't have to initiate anything. It just, so irrespective of the time taken, the fact that the reaction took place, we say it is spontaneous. So this is, why is a reaction spontaneous? Why at all is a reaction taking place is what we are trying to understand from the concepts in thermodynamics. So this is the agenda that we have while we are studying this chapter. Definition of thermodynamics. It is a study of quantitative relationship between. So, first, the whole definition has two parts. What are the two parts that it has? The two parts that it has is, it is a study of, quantitative relationship, is a study of quantitative relationship between heat and other forms of energy. Between heat and other forms of energy. The second point is, it also includes the study of heat changes. It also includes the study of heat change during physical and chemical change. So the whole gamut of study of thermodynamics is that you have taken heat. How do you get heat? You burn a fuel. And then because energy can be converted from one form to another. That's a statement we have always said, law of conservation of energy. It may not be true in one case, that we will see later on. But one thing is that this is something which we have studied from our earlier days, that energy can be converted from one form to another. So that's what we are talking. It's the word quantitative here is very, very important, because you have to quantify. We are quantifying this every day. When we are driving a car, the first thing when we have to buy a car, what is it that a question we ask? Per liter of petrol, how many mileage will it give? If some car manufacturer says 8 kilometers and some other says 25 kilometers, you are going to choose the fellow who is selling a car which gives 25 kilometers per liter of petrol. The reason is because you are quantifying that here I am putting a chemical fuel which will get converted to heat energy, and that heat energy is going to be used for what? For driving, for causing the mechanical movement of the vehicle. So we are estimating, okay, we have put this much, so how much we should get. So we have put a chemical fuel which is ultimately going to get converted to heat energy, and from that we are converting it to mechanical energy. Is this clear? And also we are going to study physical changes like melting, boiling, sublimation. There is some heat change involved in that, and these values are required for certain other purposes. Is this clear? So these chemical change, we have to decide, I want to send a rocket. Okay. Now I cannot say like I will use rocket, I will use coal as a fuel, I will send it up. You can't. Because coal does not give that much energy that it will give thrust to the rocket. Newton's third law for action is equal to reaction. The hot gases coming out is pushing the rocket up, but the hot gas has to come out with that much thrust. Is this clear? So it gives the up thrust. So which you will, then what you will do, you will decide, I need the fuel which gives maximum calorific value per gram. What is calorific value? Heat evolved per gram. And which is that? That's a multiple choice question in the exam. Hydrogen. Our simple hydrogen has the highest calorific value as a fuel. That's a question which has been asked. Hydrogen, methane, butane, pentane. All hydrocarbons are also fuels. So people may neglect hydrogen because per gram, that's called as calorie, it gives maximum energy. So if you have to choose a rocket fuel, you will go for what I call hydrogen. But if you have to just cook at home, hydrogen has its own disadvantages. Handling hydrogen becomes difficult. You would rather use. Now, between methane and butane, again, see, LPG cylinder is butane. What comes in piped gas here, this is methane. So we can choose which is going to give more calorific value. Heat per gram, energy per gram, that's calorific value. So here, so it's a combustion, and we are trying to find out, it's exothermic. We are trying to find out how much is the energy change involved in that. Okay. Now all these sweet things look very, very good about thermodynamics. But what are the drawbacks of thermodynamics? The first and foremost drawback of thermodynamics is it deals with macroscopic properties of matter. It deals with macroscopic properties of matter. See, the dictionary definition of what is macroscopic properties. Macroscopic properties are those properties which can be measured, by an instrument. So I'll now give you an example of what is a microscopic property and what is its macroscopic property. See, we have temperature. So what is basically temperature? It is the kinetic energy possessed by each and every molecule. So if I say that this has got a temperature of 18 degrees centigrade, correct? So temperature is a macroscopic property. And what is a microscopic property which we cannot measure? Those properties which we cannot measure. So that is a kinetic energy. So molecules here are vibrating like this, or and then that's creating some energy. Those energies you cannot measure. Those are microscopic properties. There is no instrument to measure that. But consolidate all the energy present is given by the heat capacity. What is heat capacity? mc theta. And the total energy is heat capacity mc theta. And that is indicated by the temperature. And temperature can be measured with the help of a thermometer. Then we have pressure. See, what do you mean by pressure of an enclosed gas? The definition of pressure of an enclosed gas is, it is the number of molecules or particles of gas heating against the surface of container. So sum total of all the molecules hitting against the surface of container is the pressure of the enclosed gas. And pressure can be measured. See, if it is atmospheric pressure, it can be measured with a barometer, and change in pressure can be measured by a manometer. That's a macroscopic property. So pressure is a macroscopic property. But if I were to ask you, okay, what is the force exerted by one molecule on the surface? You cannot do it. We are having a collective value. So microscopic properties, the force exerted by one particle, that you cannot measure. But a collective force exerted by all the molecules on the surface of the container, we now call it as a macroscopic property. It is pressure. Then we have a concept which we are going to study in great detail called as entropy. See, entropy means entropy. What is the entropy? Entropy is a total disorder of the system. Suppose if I heat ice, When I supply energy to ice, what happens? The molecule absorbs that energy, each molecule absorbs that energy, and then what happens? It frees itself to become water. It's overcome the intermolecular force of attraction, frees itself. So we say it has become disordered. Now if I heat the water further, it's going to become steam, water vapor. So what is going to happen? The disorder is going to increase. So the collective disorder of the system of the molecules, collective, total will be called as entropy. But if I ask you what is the disorder of one molecule, you cannot say that. You cannot say it because the disorder exists. But disorder of each molecule cannot be actually quantified, cannot be quantified. But a collective, the collective, what do you call, disorder, we can calculate. How can we calculate? Simple. We just find out what is the amount of heat we supplied to cause the disorder and at what temperature. Ratio of that will give you the disorder. So collective disorder can be calculated. So your disorder, collective disorder, which is called as entropy, is a macroscopic property, whereas disorder of each molecule will be a microscopic property. The second point about what do you call drawback of thermodynamics, it concerns only, or it is concerned only with initial and final states, and it does not talk about the final, and is not concerned with the path taken. So you see, if I tell you come on heat water from 18 degrees to 100 degrees, you are just going to heat water from 18 degrees to 100 degrees. You are not going to worry how much time it took. You are not going to worry how much time it took. It is clear. Whatever means you use, we are only bothered that there should be a change in the temperature from 18 degrees to 100 degrees. So thermodynamics does not specify any method. Okay, please do this to change the water from 18 degrees to, a path is not defined. A path is, your goal is what? Just to change from initial to final. I just say pour the water out from the bucket. So there is a change in volume. There is a change in volume. I am not telling you that please remove one drop at a time. Or, take some time, say 5 minutes, do it in 5 minutes. You just can pour it out just like that. The volume change has taken place. What? The question was, pour the water out. That means 28 liters, make it to 0. Fine. You just made the 0. There is no time factor over here. There is no time factor over here. It's clear. So path is not defined. Then the most third point is what? Thermodynamics does not give any idea, of rate of reaction. See, thermodynamics can tell you that this reaction will take place. But thermodynamics cannot tell you how much time it will take for the reaction to get completed. So you take phosphorus, take it out of water. It just burns immediately, spontaneously, and what happens? It becomes phosphorus pentachloride. Take an iron rod. If you look at the calculation, thermodynamics says if you keep iron rod out in the rainy season, it becomes wet, it is going to corrode. It's going to become iron oxide. It is a reaction which is happening on its own. It's a reaction which is happening on its own. It's a spontaneous reaction. The word spontaneous does not mean instantaneous. This is a problem. Instantaneous is just this now. Abhi, now I want it. Spontaneous means it happens on its own. That's the thermodynamics meaning of the word spontaneous. Okay. So it happens on its own, but it takes 6 months. It takes 6 months for the iron rod to rust. Thermodynamics says the reaction will happen. How fast the reaction will take place, that is chemical kinetics. That's the next chapter. Are you understanding? So these are the problems of what you call thermodynamics. Now we are coming to a very important part. That everything around us revolves around this simple fact that heat is being converted into mechanical energy, and then from mechanical energy to other forms of energy. So the basic starting process of thermodynamics is that heat is converted into mechanical energy. You say, sir, where is heat being converted to mechanical energy? Look at it. No? You have coal being fired, water converted to steam. Steam is being used to run the turbine, and the turbine creates electricity. So, you heated coal, you caused a physical change, the steam rotated the turbine, so there is mechanical energy, and that was connected to it is a generator, and then it converted to electric current or electricity. Your car, you put chemical fuel, petrol, diesel, is clear, that burnt, and the heat generated made the car to move forward. It's mechanical energy. So everything is revolving around this small thing. And why is it important? That's the most important thing. Because this is a process. Conversion of heat into mechanical energy is not 100% efficient. This is a process which is against the law of conservation of energy. Because we very confidently said that law of conservation of energy from one form can be converted into another form. But this is where heat energy cannot be converted into mechanical energy. 100% means fully or completely. Okay. Now how is heat converted to mechanical energy? The machine which does that is called as engine. The machine is called engine. See, you try to understand, this is not there in the textbook, but I am explaining this because this becomes the basis of complete thermodynamics. Your complete concept of work, energy, all that, there if you just say consider a cylinder, consider a piston, you will be scratching your head, what is this cylinder and what is piston? Okay. So what we have over here is the machine is called as engine. Basically there are three types of engine. One is a steam engine. The second is a heat engine. Heat engine is further divided into what? A petrol engine, and a diesel engine. And then we have third is a jet engine. Third is a jet engine. You will be surprised to know that if a multiple choice question is asked on this, you will be surprised to know that it is a steam engine which is most efficient. It's not 100%, it's most efficient, understand the language. And jet engine of course is the least efficient, that's why it consumes a lot of fuel. But the problem with steam engine is that you have to have a coal, water supply and all that in a ship. It becomes very difficult. In those days steamers used to come. So steamer could come from England to India so quickly because their engines were very efficient. So they could. Whereas what we now talk about or what we are using common today is a heat engine. In our day-to-day life, we are using a heat engine. Heat engine is of two types. What are the two types? One is a petrol engine and the other is a diesel engine. So how does a petrol engine work? Okay. See, in a petrol engine, what happens? Basically, engine is nothing but a huge block of metal, aluminium, basically. It's huge block of aluminium metal, in which cylindrical holes have been made. Cylindrical holes have been made. So you have a one cylinder engine. You can have, what are the words you are going to hear in your day-to-day life? So heat engine, you say one for A. You have a one cylinder engine. Your motorbikes have one cylinder engine. Then B, you could have a 3-cylinder engine. So the small cars like Alto, Volto, all these have, small cars have 3-cylinder engine. SUVs, so they will have a 4-cylinder engine. So I can say SUVs, big ones, more power, no? Now what is a cylinder? I told you, simple. You have a metal block. You have a small metal block in which one cylinder is made. You become one cylinder engine. A little bigger block, make 3 holes, 3 cylinders, 3-cylinder engine. Take a bigger block, because I mean it's quite bigger block, means it has a weight. It has a weight of 950 to 960 kg. Like for example, a Wagoner has engine capacity, engine weight itself is about 950 to 960 kg. So you can imagine the weight of the car is basically weight of the engine. So what happens is, now what is this engine? So I'm going to teach you how it works. Petrol engine and a diesel engine. So in a petrol engine, there are 2 types of petrol. One is called a 2-stroke engine and the other is 4-stroke. 2-stroke is just 1-2-1-2. But these days 2-stroke engines have been banned in India because it releases too much of carbon monoxide. Your very old auto rickshaws were 2-stroke engines. Now everything has been converted into 4-stroke engine. So we are talking mainly about 4-stroke petrol engine. So what happens is, see, you have 1, 2, 3, 4. So this is the cylinder. What is a cylinder? It's a simple hole, cylindrical hole made in a metal block. Now the cylinder contains a piston. So this is one cylinder. With that we are explaining what are the 4 strokes. What is the explanation? Petrol engine, explanation for 4 strokes. Explanation for 4-stroke such that heat energy is getting converted into mechanical energy. So what happens is, you have a piston. So you have a piston, you have a connector, and this connector is connected to a crank, and at the top you have points. So this will be the this will be a spark plug. Sorry, this will be a inlet. This will be a outlet, a exhaust valve, and you will have a spark plug. So all the 3. First I'll draw so it will become easy. Okay, first I'll draw it, then I can explain very easily. So then this comes here. What are the strokes? First, what happens? So, let us discuss what these, what do you call, are. So, this is the cylinder. This is the cylinder. This red one is piston. This is your inlet valve. This is your spark plug. And this is your exhaust valve. So in stroke 1, sorry. So in stroke 1, what happens is inlet valve open. Inlet valve opens. Okay, outlet valve, exhaust closed. So what does the inlet valve pour into the cylinder? Inlet valve pours into the cylinder a mixture of air and petrol. Mixture of air and petrol. So this is how a piston looks. I have a piston with me, so I can show you. See, this is a piston. Basically this part, I think now I can get a better way. See, this is the piston. This is piston which when I had done my engine work for my car, I had kept it just to show to the children. It's a piston from Wagoner. So this is a piston and this is the connector. So you have the cylinder like this. So suppose you can imagine like this. Now, this is the, my hand will be the cylinder. So what happens? The piston goes down, piston comes up, piston goes down, piston comes up. That is the mechanical work. Okay. And what happens when it goes up? This connector, see, when it goes up and down, this connector is connected to a crank. So the crank moves. So crank is like this. The piston goes down, the crank moves down. So like this. So what happens? So this piston moving up and down like this is causing the crank to move like this, and that crank is sent to the axle, and from the axle the mechanical energy is transmitted into the wheels and the wheels move. Is this clear? So it's basically gears then we have, to do all that work. I'm not going to the depth of that. So this is a piston. Okay, this is what I'm saying. So in the first stroke, what happens is you have the cylinder. Okay, so from here what happens? Air and petrol mixture is poured. So immediately what happens? Because of that, the piston moves down. That's your first stroke. So your inlet valve is open. Now what is the second stroke? The inlet valve and the exhaust valve both close. Very interesting thing I am teaching you today. So in the second stroke, stroke 2, in the stroke 2, inlet valve closed, outlet exhaust valve is also closed. Then what happens? This spark plug gives a spark. It's just like a gas lighter. How we use a lighter? It's just a spark. It just gives a spark. Okay, the piston moves up, compression, and what happens? Moment the spark plug gives a spark, the petrol catches fire because there is air supporting it. Moment it catches fire, what is going to happen? Stroke 3, the piston is going to move. So what is going to happen? Try to understand. So first was, see, your piston went down, then the piston came up. When it came to this stage, okay, here the spark plug gave a spark. When the spark plug gave a spark, the piston moved down, third stroke. Okay. So what is stroke 3? The stroke 3 is inlet valve closed, IV closed, exhaust valve closed. That builds a huge pressure. Na? When it builds a pressure, the piston goes down. That's the third stroke. Now what happens in stroke 4? Exhaust valve, inlet valve closed. But exhaust valve opens. So moment the exhaust valve opens over here, what is going to happen? The pressure is going to be released. No? All the gases, hot gases will move out and will be thrown through the exhaust pipe. But what is happening inside? There is vacuum created. Na? If the gas is going out, it's creating a vacuum. So the piston moves up again. That's the fourth stroke. So understand, 1, 2, 3, 4. So this creates one full motion. This creates one full motion on the crank. So this continuous 1, 2, 3, 4, 1, 2, 3, 4. How is this 1, 2, 3, 4 created? Because petrol is burning to create heat energy. Heat energy, what does it do? It increases the pressure of the gas inside. Where is the gas? The gas is air, carbon dioxide, nitrogen, whatever is there, all these mixture of gases. It increases the pressure, pushes the piston down because of the pressure. That's how enormous the pressure is. That this heavy, it's quite heavy, I'm telling you. This heavier piston is pushed down. Okay. And then what happens? Because of release, again you are able to push it up, creating vacuum. So this continues, this is a four-stroke engine. So here essential component is the fire is set alight by what? By the spark plug. You have what you call petrol air mixture, but it burns because you get a spark plug. Now let's come down to diesel engine in the same way. So we talk of diesel engine, what happens? I'll first draw 1, 2, 3, 4. Okay. So what happens? In a diesel engine, now you try to understand that you have inlet valve, you have an exhaust valve, and you can have a heater, no spark plug. Okay. Then so this is inlet valve, this is exhaust valve, and what do you have? Your piston. So what happens is, same way, stroke 1, stroke 2, stroke 3, and then we have stroke 4. Now let me explain. So one very important difference between petrol engine and diesel engine is that diesel engine does not have a spark plug. It does not have a spark plug. So obviously then the mystery remains, what is causing the fuel to burn? I'll explain. So what is stroke 1 here? The inlet valve opens. The inlet valve opens. It is clear. Exhaust valve closed. And from the inlet valve, hot air is coming in. Hot air is poured. And then what happens is, moment you push hot air, the piston is going to go down. This is the first stroke. Then what happens is, from this, we put hot diesel. And after putting hot diesel with the hot air, there is a heater actually. There is a heater through which the diesel passes, and that hot diesel is poured in. And while diesel is getting poured, we are also compressing it. So your second stroke is compression. Let's put it this way. So your stroke 2 compression. Now there is a concept. What happens is, listen. Now you have taken hot air and hot diesel. Diesel vapor. Diesel means not liquid diesel. Diesel vapor. Both are gases. And when you compress now, what happens is the temperature of this mixture increases, because the energy is getting, the compression energy is also getting used to convert into heat energy. So temperature increases. We learned this in first law of thermodynamics, mathematical expression. And when the temperature of this mixture increases, it comes to a certain point which is called as flash point. Flash point is that temperature. See, flash point is that temperature flash point is temperature at which a fuel catches fire or burns. No need to put matchstick, no need to put candle, nothing. So as the temperature goes on rising, it reaches the flash point of diesel, and diesel burns, and there is hot air anyway available. When the diesel burns, so here what happens? For this to happen, both your inlet valve closed, exhaust valve closed. So moment diesel burns, the heat supplied is going to be used for expansion of all the gases inside. Leftover air, carbon dioxide, nitrogen, everything that is there. And that is going to create a lot of pressure. So when it creates a lot of pressure, the piston moves down. Again, in this case, this is stroke 3. What is going to happen? Inlet valve closed, exhaust valve also closed. Then what happens? The exhaust valve opens. Stroke 4. What is stroke 4? Happens automatically. What happens? Inlet valve is closed, but exhaust valve is open. So moment you open the exhaust valve, there is vacuum created. Now the hot gases are moving out. So the pressure on this is less. So vacuum is created and the piston moves up. So here what happens, see, first stroke it goes down because of the hot air. Then second is compression, while hot diesel is mixing with what you call the hot air. And when this is happening, what happens? The temperature of the diesel is increasing to its flash point, to its temperature at which it will burn. Then what is going to happen? That moment it reaches flash point, it starts burning. So it's going to expand. It's going to cause the heat release is going to cause the expansion of gas. That is going to push the piston down again. Then what is going to happen? The exhaust valve opens, hot gases are going out, so the piston moves up. So that is how the 4 strokes are there, and this is how. Now the most interesting part is the first thing that I told you, heat is converted to mechanical energy. See, in case of petrol engine, the efficiency is nearly 32 to 38%. And this is about diesel engine efficiency. Is about 48%, 42 to 48. So you can see 100% conversion is not there. So if you really try to find out that I supplied so much of heat energy by what you call burning petrol or diesel in the cylinder fitted with a piston, and then I measure the mechanical work done by the movement of the car, I will find that petrol engine is less efficient and diesel is slightly more efficient. That's why you see, from the point of view, people prefer diesel vehicles. People prefer diesel vehicles. But then of course what we have done is, so this is what the whole study is about. This what I taught in a later on part of this chapter. What am I going to do? I am going to derive how much is the work done. I said arbitrarily 30 to 30%, but how much is the work done? We are going to have, and we are going to have a equation, how much should the work have been done theoretically. See, you cannot say maximum work this much should be done. That cannot be found experimentally. Why? Because it was found experimentally 100% work is being done by some engine. We are not fools to use these engines. Now we will throw this away and use that. There is no engine which is 100% efficient. But we can mathematically find out what will be the maximum work done by this cylinder piston combination and what is being actually done. And so we can calculate the efficiency. So that is what is the first part of the work that first part of the story that we are going to do in this chapter. It is clear. And for that we need to know this. Okay. So you should know, because here there is a problem, because there is a question which is asked. It is clear that you have a gas to which heat is supplied. So what happens is this, generally many people are learning, being taught that moment you supply heat to a gas, it is expansion. You supply heat to a gas, it is expansion this way. But that's not so. If you supply heat and if you compress, that possibility also exists. So at that time the student may think that this question is wrong. How can you supply heat and cause compression? Yes, you can supply heat and cause compression. The effect of that is the temperature of the air fuel mixture is going to rise. And why it is going to rise, that we will mathematically see when we talk about mathematical expression of first law of thermodynamics. But this is what we are talking. The whole thermodynamics is about quantifying the work done. Quantifying the work done and finding out how much should be done, because all heat energy is not converted into mechanical energy. It's the exception to law of conservation of energy. It is clear, this is exception. That heat energy is not converted into what you call, all heat energy is not converted into mechanical energy. And what happens to the heat energy, the remaining heat energy? That is taken out of the engine through the cooling liquid and then taken to the radiator where there is a fan which throws out. That's why you see cities are having more heat wave than villages. There's so much of automobiles that we have. They are throwing out so much of heat. Imagine 60% of the petrol that is burned is being thrown out as heat energy outside. So temperatures have increased. So automobile pollution of nitric oxide is different. This is also another pollution. The average temperature is higher. So Bombay has this problem. Our average temperature is higher than many other places, or what it should be, because of the automobiles. Every automobile is moving. You put 1 liter of petrol, so costly these days. It is clear. Imagine 60% of his heat is being thrown out. But then we realize that some cars are a little more efficient and some are what you call less efficient. So how did these people increase the efficiency? The engine is the same. Here they used physics. Here they used physics. See, we have what we call as multi-point fuel injection system, MPFI. So what is this multi-point fuel injection system? Earlier what we had was just a carburetor. It simply spewed, went on, whether you're starting the car, whether you're driving the car, whether you're stopping the car, same amount of air fuel mixture was being poured, literally poured into the engine. So it was inefficient. So what spews is a carburetor, old. Now we have an injection system. Injection system is smart, machine learning. So you have a chip inside that in which a program has been made. What the program has been told? Monitor the fellow. See, in physics, what is inertia? Inertia is tendency to remain in a state of rest or motion. So when you want to start a car, the car is having inertia. It is in a state of rest. It is in a state of rest. You want to move. You have to force it. So maximum energy is required to start. So that's why if you see when you're driving, they always say that when you're starting the car, don't press the accelerator. Why? Because the injection system, the program has been made that when you're starting the car without the foot on the accelerator, it knows that the car is at rest. So what does it do? It has a solenoid valve. It opens the valve for petrol to a larger extent and air to a smaller extent. So more petrol is put. So more petrol is put, more force, more thrust we get, the car starts. Once the car starts, now what is the inertia? It is in a state of constant motion. Now you have to only give that much petrol. You press the accelerator. What happens? It starts reading. You have pressed the accelerator. The car is in a state of motion. So the petrol valve constricts and the air valve expands. So there's rationing of the petrol which goes in. So by rationing the petrol, what happens? We save petrol and then increase the efficiency. Had it been carburetor, you would have got difference is efficiency is huge. A carburetor based car will give you only 8 kilometers per liter. The small cars fitted with this MPFI, multi-point fuel injection system, they give 25 kilometers. So that is the difference, without AC of course. That is the difference. So they have not changed the engine. Engine remains the same, but they have only rationed out the petrol when it is not needed. Because when a car is in motion, it only needs energy or force to overcome the force of friction. That is less. So less petrol is given to the engine. Again when you stop, then again what happens? You need more force to stop, more petrol, less air. That's why in cities you get less efficiency. Why? Because it's continuously start, stop, start, stop, start, stop. Whereas if you go to highway, there is no start, move, stop at the destination. So efficiency is more. This is clear. So this is what we are going to learn in thermodynamics. What is it that we are going to learn? Here is a cylinder and a piston. So a combination of cylinder and piston is an engine, and what that they don't tell in the textbook. They just go on saying cylinder piston. You are breaking your head. What is this? A cylinder piston combination is an engine, and what does the engine do? The engine converts heat energy into mechanical energy. And what is the scope of our study from the next lecture?